Okay, welcome everyone to my continuation of what is algebra. Well, today's topic are fields, or to be more precise, maybe I'm going to talk about mostly about finite fields. And I kind of want to explain why fields are rare. So fields are certainly one of the main objects under study in something like Galois theory. So Galois theory is basically about field extensions, so extensions of certain fields. And it turns out that fields are, in some sense, well, slightly ill-behaved algebraic objects, which is a pity, or, of course, you can say, well, that makes them interesting. So let's just jump right into it. So first slide, fields are a bit weird. I don't want to diss those poor fields. They're still very nice. But anyway, so let's start by recalling basically the definition of a field. We will see it on one of the later slides anyway, just to get us all on the same page. So a suitable definition of a ring, and the only thing to stress here about what I mean by suitable is that I want some funny condition like 0 is not equal 1. So I want at least two elements, which are called 0 and 1. Anyway, and then a field is the suitable definition of a ring, plus this kind of strange and asymmetric condition that every element not equal to 0 is invertible. So 0 is not 1, 0 times everything is 0, so 0 can't be invertible. And you want to have this funny, slightly weird condition that every non-zero element is invertible. And of course, all of you know examples. Z is not a field, 2 is not invertible in Z, but Q is a field, of course. And some other funny examples. Z mod 4 is not a field. Why is Z mod 4 not a field? Because 2 times 2 in Z mod 4 is 0. So 2 can't be invertible. So as soon as you have an element that is so-called nilpotent, A times B equals 0 for A and B non-zero, and they can't be invertible. With contrast, Z mod 3 is a field. Just to get us all on the same page, just keep those examples in mind. Q and Z mod PZ for P being a prime. And then you make some comparison of standard algebraic objects like groups, vector spaces, rings, something like that. And you look at the collection of them. Let me say the world. A more fancy term would be the category. But anyway, so there's a kind of a collection of them. And you would realize that, for example, something like products exist in rings. So if you have a ring R and you have another ring S, then you can do something like a tuple construction and you get another ring R cross S. You can't do that for fields. So if you have a field K and you have a field K prime, then this is usually not a field. And the reason is pretty simple, because an element like 0.1, so here multiplication is component-wise. This is a zero divisor because, well, if multiplication is component-wise, then this thing multiplies to 0, of course. This is no problem in a ring because you don't have this asymmetric condition, but this is a problem in the field. So here exists, check, do not exist, bad. Similar things like you always can map from Z into any ring, it's so-called initial ring or initial object, and you can always map to the zero ring. So initial and terminal objects exist here, no analog. You have some notion of a free ring, which are polynomials. Polynomials are really, really important. There is no notion like a free field. I shouldn't make a check here. I should do this. So in some sense, the world of field is algebraically really weird, which you can now say, oh, that's bad. I don't want to study fields. Fields are strange. Or you can say, ooh, this is cool. Fields are interesting. So let's study fields. But anyway, keep in mind that fields are a bit special because of those slightly asymmetric properties you would assume on a field. Let me recall them, or let me repeat them. It's this funny property that 0 isn't equal 1. That's already a bit strange. But anyway, and even more crucially is that every non-zero element is invertible. It's kind of a weird property. And it forces some kind of strange things to happen, like a product construction just doesn't work for fields, at least not in any naive way. So let me show you how, in some sense, fields are extremely rare, because that's what I try to sell here. So, and kind of the most important fields beyond the extensions of Q, which play a crucial role in Galois theory, something like the real numbers, which you would see in something more like analysis, or the complex numbers, which you would see in more like complex analysis. So those fields, then there are also the finite fields. And the finite fields are sometimes called Galois fields, and they're constructed as follows. So a picture like this, I will explain the picture in a second using Mathematica code linked in the description. So this is a picture of the multiplication table of z mod 17z, which is one of the finite fields. And it looks pretty nice. The colors indicate, we will see it. The colors indicate the different elements here, and it looks pretty regular. And you can construct the finite fields as follows. Well, I'm not making any statement right now, but exact existence. So you know that z mod pz, for p being a prime, is a field, and obviously the order is p. So this has order 17. Okay, here's the picture. So yeah, and what you can do then is you can take some prime power, you call it q, and you take the polynomial ring, and you make sure that you have an irreducible polynomial of the degree. So q is p to the k, and you have an irreducible polynomial of that degree. You take the polynomial ring, you divide by that irreducible polynomial. Polynomial ring modulo an irreducible polynomial. That's a field, and it turns out that this field is of order q. So q, keep in mind, q in my notation is always p to the k. So we just have constructed a field of order p to the k for all p and all k, which are those Galois fields. Yeah, so let's have a look at Mathematica. So here's Mathematica, and what you see is just a multiplication table. So I can vary here my field size. We'll go to that in a second. I can vary here my pixels, so I can make it bigger or smaller. And yeah, and I can go from multiplication to addition table. But let's say stay with the multiplication table. So this is, well, z mod 2, and the color code is just indicating the two different numbers. So white is always 0, and the black is in this case 1. And of course, 0 times anything is 0, so you see those, well, white things here. For z mod 3, you will see the same. And 1 times 1 is 1. Let's have a look at this. 1 plus 1 is 0, right? So you can vary it. If you want to play around with it, as I said, it's linked in the description. And then you can do the prime numbers, and you always see those nice patterns. So the one I showed you was 17, and the color code is just 0, 1, 2, 3, 4, 5. So a lot of grayscales up to 16, which is very black. And this is how the multiplication table looks like. Okay, you can do that if you want to. Here's another one. 11, whatever, addition table, multiplication table, whatever. And then I just explained that we also, for example, it looks a bit crazy, is you have a field of order 2 to the 4, right? So you take a degree 4 polynomial, x4 plus, for example, this one, which is irreducible, you quotient out by it in the polynomial ring, and you get a field, and this is how it looks like. Okay, whatever. And you can vary the polynomial if you want. You get slightly different things, but actually they are isomorphic, which is a non-trivial result. For different polynomials, they will be isomorphic. But basically what you do is you take your degree 4 polynomial, and you can construct the field of the corresponding size, in this case, of the size 2 to the 4. Let's go to 5 squared, for example, same pattern. Now your coefficients are from z mod 5, and you can take some irreducible polynomial of degree 2. They're apparently quite a lot. You take this one, and you get a field. And those ones that you get are the so-called Galois fields. And as I said, I just state existence here, because polynomial ring modulo an irreducible polynomial is a field. What I don't state here is uniqueness. As you have seen, it's in the Mathematica code. If you really take a different irreducible polynomial, at least the multiplication table looks different, turns out that still all those fields are isomorphic, which is a non-trivial result anyway. Okay, so let's have an example of infinite fields that you can construct from Galois fields that are important in algebra. The algebraic closures of Galois fields. So algebraically closed just means any polynomial you can write down has a root in your field. Not examples are something like Q and R. They are not algebraically closed because I can write down those polynomials, for example, x squared minus 2. This is for Q, which would have square root of 2, which is not a rational number. For R, I could write down something like x squared plus 1, which has, for example, root I, which is not a real number. With contrast, this guy is algebraically closed, which is kind of the fundamental theorem of algebra. And the question is, well, we have now these Galois fields. We know that they exist. So what on earth can we do? Are they algebraically closed or not? And they're not. And here comes proof that a finite field can never be algebraically closed. So you always have a polynomial which doesn't have a root in your finite field. And the proof is so ridiculously simple that I actually put it on the slide. It's very beautiful and very easy to remember. And yeah, so you basically use the fact that you have a finite field. You take the product over all x minus a, where a runs through the elements of your finite field, which means this green box here is a polynomial which has all elements of your finite fields as roots. And that's how it's constructed. It's a product of x minus element. And then you add 1. And because the green box has everything as a root, if you add 1, this polynomial doesn't have a root. Proof done. QED. A finite field is never algebraically closed. And the procedure to construct the algebraic closure of those finite fields is this one. So just take all of them together. So basically what you do is, well, you construct these by, you find your irreducible polynomials. They can't have roots. They're irreducible. You just add artificially the roots of those polynomials, and you keep on going until there are no irreducible polynomials anymore, which kind of is his existence proof. And a bit more tricky is to see that actually this construction is unique, and it's with the property of being kind of a minimal algebraic closure of a field. But anyway, so the algebraic closure of those Galois fields is just take all of them together, and yeah, well, they are just not they're just not finite anymore. That's kind of the point. Okay, so what is a field now? A field, as I said, is just a set with two elements that are not equal. Let's call them 0 and 1, together with the usual properties of what you would see as a ring. So we have two operations, an addition and a multiplication. It's an abelian group with respect to addition. It's an abelian group with respect to multiplication. Oh, almost. It's not an abelian group with respect to multiplication. Everything except 0 is invertible, which is this asymmetric condition I was talking about before. And of course, you want that the two roots distribute over one another. And so it's a ring with this asymmetric condition of every non-zero element being invertible. And the examples you should keep in mind are, well, Q bar, so the algebraic closure of Q, R bar, which is C, which are kind of the classical examples you see in a first class on whatever linear algebra. Those funny Galois fields and the algebraic closures. So the finite field extensions or infinite field extensions of Q, which you usually study in Galois theory. So there will certainly be a lot of videos about them. And there are more fancy examples like p-adic numbers, which I'm probably not going to touch in a series on algebra. Let me just mention here that Q bar is not equal to C, for example, because something like pi is not in Q bar. So in Q bar, you really just take all polynomials and you throw in roots of all polynomials. That's what I just explained for the Galois fields. And pi, for example, is not a root of any polynomial, which is, by the way, not easy to see, but that's a, well, let's say it's a fact of life. So q bar is not equal to c. So q bar is a field on its own. And algebra is more or less studying those things. Like q and q bar are nice fields for algebra because kind of they mimic the operations you like in algebra, like polynomials and roots and so on. While things like pi are a little bit complicated from the viewpoint of algebra. Anyway, I'm starting already to waffle. So this is maybe this and this are maybe the main examples you would like to keep in mind. So Galois fields and fields extensions of Q, which are kind of the main objects in under study in Galois theory and first class on algebra. So slogan of this whole video is fields are rare, which is not quite true. So let's first of all have a look at the bottom theorem. And then we have a look at the top theorem. So the kind of the top theorem is from the viewpoint of algebra, the importance theorem. Of course, you can't really tell what is an important theorem or not, because it really depends. But anyway, from the viewpoint of algebra, the top one is certainly more important than the bottom one. Just to be sure, because I want to sell the slogan, the fields are rare, there are quite a few fields. So the theorem is for any cardinal, there exists a field of that size. So basically, if you don't know what a cardinal is, it's kind of a measure for very, very large sets. So what you can do is, for example, you can always take some crazy infinite field extensions of Q. So basically, the statement down here is that there are a lot of fields. Right? The class of fields is an honors class. It isn't a set anymore. So there are a lot of fields. But in some sense, all of these are unimportant, and you kind of completely ignore. Well, I shouldn't say that, but let's just say it anyway. So you can completely ignore the bottom. And what is more important is this idea that fields are pretty rare. So they are like Galois fields or field extensions of Q, and then you're basically done. Because, well, we have Q bar, which let's say is a field extension. It's not a finite field extension, but it's certainly a field extension of Q. And with R, you can't play many tricks anymore because you have R bar, which is already C, and that's about it. And all other field extensions that you can do from R are a little bit silly in some sense. So the point is that fields are pretty rare. So there's those Galois fields, there are Q and finite field extensions of Q, and that's about it. And for Galois fields, the statement is actually really nice and a bit surprising. So I already told you about the existence of those things, which isn't completely obvious, as we have seen in the Mathematica code, it's really not obvious, is that actually they're all isomorphic. So for a given order, there's exactly one field of that order. In other words, take any irreducible polynomial, the field you get will be always isomorphic if you fix the degree of the polynomial. And it's even better as a statement, there are no other finite fields. So Galois fields are just all finite fields. There are no other finite fields. There is no finite field of order 6, for example, because the only possible order for finite fields are prime powers. And there are not many prime powers, right? Of course, if you start with small numbers, you see a lot of prime powers. But if you're very far out on the number line, there are basically no prime powers anymore. So that's why I wanted to say that fields are pretty rare. And these are, of course, well, maybe not of course, but these are of crucial importance in algebra and, what a surprise, in Galois theory. Anyway, let me wrap up. So field is kind of the slightly asymmetric definition of a ring with all non-zero elements being invertible. Let's also assume that 0 is not 1, so it has at least 2 elements. And the category of fields, or the world of fields, is a little bit ill-behaved, algebraically speaking. Fields are a little bit ill-behaved, and you don't have too many of them. For example, finite fields are in one-to-one correspondence with prime powers. And it's kind of a miracle that they are so interesting to study in the end. And the point of Galois theory will be to study those funny blossoms that you see, the finite field extensions of either the finite fields extensions of finite fields, or of Q. Yeah, but that's about it for today. So I hope you enjoyed the video, and I also hope to see you next time.